نتوكل على الله ونقول بسم الله الرحمن الرحيم. دقيقتين زي ما تأثر، أنا أوج من الانتظار وأنت حضرتك دا تطور من الانتظار، ضجت من الانتظار.
لا بالعكس، ما عندي أي مشكلة يعني.
نيفر، ماكو مشكلة.
بسم الله. السلام عليكم.
السلام عليكم. مرحبا دكتور.
عليكم السلام ورحمة الله.
أهلا دكتور، حيا الله الجميع.
حيا الله.
إذا تحب تسجل دكتور لؤي، إحنا ما أدري السيد رئيس الجامعة يجي لو لا دكتور نصري تعرف؟
ما أعرف، ما عندي علم. أنا ما عندي علم، ما عندي. بس
بدينا تسجيل دكتور.
هو بلش تسجيل، بس السيد رئيس الجامعة أعتقد إنه اللي أعتقد إنه خطية جوب عليه كل شيء هواي بحكم يكون مؤتمر مال الجامعات التقنية جدا، والتهيئات والاستعدادات على قدم وساق هو والسادة المساعدين. فما أعرف هل عنده وقت يسمح إنه يدخل معانا ولا لا. إحنا نتوكل على الله. صارت الساعة 4 تقريبا، just 1 minute، مو مشكلة. نقول بسم الله الرحمن الرحيم. إذا يسمح السيد رئيس العميد، سيد العميد.
بس إذا تسمح لي دقيقة واحدة دكتور نصري، شكرا جزيلا. بسم الله الرحمن الرحيم. ضمن احنا كليتنا تعودت عندها برنامج متابعة الدارسين، وضمن هذا البرنامج اليوم نتلقى أحد محمد عبد الكريم من الولايات المتحدة. هو منتسب إلى الكلية التقنية الهندسية الكهربائية. حسب معلوماتي انه هو خلص واخذ الشهاده، والان حتى المده انتهت مالته، والان جاي نعالجها باجازات. نتمنى له التوفيق للدكتور احمد، وايضا نتمنى انه يعود لنا بسلام. احنا محتاجين لخدماته، واكيد راح نستفيد من معلوماته. وقبل ما يرجع احنا نريده يسوي لنا سيمينار من مكان عمله يطلع عليه المختصين ولتعم الفائده. انا اشكر مركز الحاسبه اللي يدير الحلقه فنيا، واشكر الاستاذ الدكتور نصري اللي حيدير الحلقه علميا، واتمنى للجميع الفائده والشكر الجزيل.
تفضل. شكرا جزيلا دكتور.
شكرا دكتور. نقول بسم الله الرحمن الرحيم. دكتور احمد، راح اقول لك دكتور احمد بعد خلص تصير دكتور.
اوكي، ثانك يو.
You're welcome. Shall we start؟ خلينا نبدأ على بركة الله ونقول يا الله. بسم الله الرحمن الرحيم. تفضل.
Good afternoon, and it's now like 1:09 morning in Eastern time, and allow me to first of all thanks Professor Nasri, who is attending on behalf of Mr. President of Central Technical University. Also, thanks for Mr. Dean and the attendances from the College of Electronics and Electrics Engineering. So let me introduce myself. My name is Ahmed Muhammad Abdul Karim. I'm PhD in Mechanical and Nuclear Engineering. I earned my degree from Virginia Commonwealth University, VCU, located in Richmond, Virginia, United States. And today I'm going to talk about the smart material and their application. Just like I will give you like little information about my university. It's established in 1838, and we have like 3 different campuses. The main one is the Monroe Park campuses, which is like usually all the colleges and schools, and mainly my College of Engineering in this campus. And also we have the MCV, which is the Medical College of Virginia, which is like usually all the medical facilities and and hospitals. And we have like VCU Arts, which located in Qatar. I don't have any information about that. So this is the total number of the students, the graduate and undergraduate, which enrolls in 2018-2019. So today I'm going to talk about the smart materials and like the motivation, goals and approach, principle of operation of non-destructive evaluation fluid, method, numerical and experimental results, non-destructive viscosity sensor, conclusion, recommendation for future work, unique contribution and application. Smart materials are the materials that have the ability to change one or more of their inherent properties related to stimuli in a controlled manner. There are several external stimuli to which the smart materials are sensitive are stress, temperature, magnetic fields, and electric fields. So right here, okay, in this table, we can see the table that shows us the smart materials, which is the piezoelectric. So we have like the input is the deformation, the output is the potential difference, which is voltage. Electrostatic, the input is potential difference, the output is deformation. Magnetostrictive, the input is the magnetic field, and the output is the deformation. Thermoelectric, the input is the temperature, and the output is potential difference. And the last is the shape memory alloys, which is the input is the temperature and the output is the deformation. Most of these materials, except for the shape memory alloys, works as a like usually fabricated and fabricated for the sensors, except for the shape memory alloy, which is usually used for the medical purposes, like such as the dental braces. Usually they use it like to remove the blocks in the vein and arteries, and I think they use in the bones to fix the bones. Right here, okay, how it works. So the piezoelectric effect usually, like when you apply like the voltage, okay, you will get deformation. It's like it's not like the like regular material. When you apply that force, you will get deformation. Right here, when you apply like the deformation, you will get voltage, and vice versa. When you apply voltage, you will get deformation. This is called like piezoelectric effect, and the first one was discovered by the Pierre Curie in 1880. And we have like another effect which is works with the magnetostrictive effect, which is if you apply the external magnetic field, you will get deformation. And we have like the piezoresistive effect. If you apply the force, you will get deformation. So I will jump to the main object, which is like my dissertation work, which is non-destructive evaluation method. So a non-destructive evaluation method is a method that used usually to detect the deformation or mechanical defect, okay, such as crack propagation, fatigue, anything, okay, related to the mechanical failure. So right here, okay, some of the research that belongs to the non-destructive evaluation, we use to, as I say, okay, like usually use it in the structure and to detect any mechanical failure. For example, like right here, okay, we see like we like place the PCT and we send a wave. So if we do have like any mechanical failure, so the wave that travel will be like the same. But if we detect any failure, there will be like any any voltage, okay, like a change. So that's why we can detect any failure in the structure. This is another, like, this is, I think, future work, okay? So right here, we can see how they, like, they place the PZT. So from here, okay, you can see, like, they detect any loose in the bolts that connect the cables in the bridge. Right here, okay, they place the PZT on the airplane. So from here, you can detect any crack or in the, like, airplane body. This is another application. So we usually use use like the PZT to separate the fluid from the solid, okay, and usually use like in the chemistry or like biology to separate the particles from the fluid. This is another application for the PZT, okay, and we can see also the separation of the particles from the fluid sample. Right here, okay, types of the PZT materials, because I'm focused totally, we do have like different types of the piezoelectric. We have piezoelectric, materials, and we have the pyroelectric materials. So the piezoelectric materials, usually they have like the common material used in the viscosity sensor, usually PZT5A, and PZT is like stands for lead zirconate titanium. So we have like PZT5A, we have PZT4, and we have PMN32. This is very important material and kind of like super expensive single structure material. And I just like when I use the simulation to use the properties for this material just for interesting, because it's super expensive material. And the main like goal for my my research, okay, to investigate the acoustic pressure and use like cheap material. Right here, okay, the direction. So I'm gonna show you, okay, how it works. So we have the polarization. When I say polarization, I mean we applied the direction of applied voltage, and we do have like X, Y, and Z. And instead of we has like used X, Y, Z, we're gonna use the nomination 1, 2, and 3, and we do have shear. We have 4, 5, and 6. So the most important, the most important parameter, it is they call it like the dielectric constant, which is D33, induced polarization in the direction of 3, which is parallel to the ceramic element polarized per unit stress. And we do have like D31. So this is the polarization. We have the X is 1. And this is the induced polarization in direction 3, parallel to the direction in which the ceramic polarized per unit stress applied in direction 1. And we do have D15, which is the induced polarization in direction 1, perpendicular to the direction in which the ceramic element is polarized per unit shear. About direction 2. Right here, okay, the properties of the piezoelectric material. I just forget to say, like, usually piezoelectric material is an anisotropic material. So, I mean, when I say anisotropic material, which is different the isotropic material, I mean, like all the material properties are changed in all directions. So right here, okay, I just go really quick over the coupling matrix, which is in a column per meter square. We do have like the D31, which is defined like in the previous slide. We do have D33, and we do have D15, and we have the relative permittivity in the direction 111, I mean XX, and the relative permittivity in the direction 3,3, and we do have like 3 different materials: PZT5A, PZT4, and PMN32. This is the motivation, first of all, to develop and explore new technique to monitor fluid properties, develop an application by building a device that can be significant effect on the healthcare industry. Goals and approach demonstrate that the non-destructive evaluation techniques can be applied to monitor fluid properties such as viscosity using ultrasound wave propagation. The approach study the effect of varying distance between the sensor and actuator, piezoelectric pair fully submerged in a fluid, study the effect of different types of piezoelectric sensor and actuator materials such as PZT4, PZT5, and PMN32, investigate the effect of varying geometries for the piezoelectric such as square, circle, and triangular. So principle of operation. The principle of operation is simply, okay, send the signal by using, we do have like PZT pair. I mean, I have like 2 PZT, one works as the actuator and the other one sends the signal through the fluid medium. So I send usually sinusoidal voltage signal through the actuator, and this will travel through the fluid medium to the sensor. Usually experimentally, you can fabricate a device to measure the signal, but due to the complexity of the geometry and the interaction between the solid and structure. It's really hard to find any mathematical and any exact solution for the problem. That's why I'm gonna use numerical solution and the mathematical and numerical model to find the solution and acoustic pressure deformation for both sensor and actuator. So usually how it works, we do have the PZT, which is the solid, and we do have the fluid domain, and simply we're gonna use the equation of motion coupled with the Navier-Stokes equation and equation of motion to solve the fluid structure interaction. And this right here with the following assumption. So the fluid is compressible. I mean, when I say it's compressible, means density change with the pressure variation. The fluid is non-viscous, so non-viscous dissipation term. The flow is rotational, no mean flow of fluid, and the change of the mean density and pressure remains small in different areas of the fluid domain. Right here, the matrix formulation for the Navier-Stokes equation and continuity equation. I have all the derivation. It's just like this is the final form of the three equations. And we can see like right here is the mass for the solid. Right here is the mass flow for the solid and structure. Like right here damping. Right here the stiffness for the structure and the stiffness for the structure. And right here Fs means like the fluid. The force that applied to the sensor, to the actuator. So the finite element method investigate the investigation of the acoustic pressure waves propagation for the three different materials of the actuator sensor piezoelectric pair with the three different geometries immersed in a container filled with the fluid, using the ANSYS for modeling the acoustic pressure waves propagation for actuator sensor piezoelectric pair. Right here, we do have like three different models with three different PZT pair. So I'm gonna go like real quick on like this figure, and we can see right here, we do have two PZT. One works as the actuator, the other works as a sensor, and we do have like this holders that hold the PZT and this wire attached, so we can measure the signals that are generated by the fluid. So right here, we do have the fluid. And there are like three different, as I said, like earlier, there are three different material. We do have like square, we do have circle, and we do have triangular to see the effect and select which one is which one is good to be select as a sensor. Right here is just the dimension for the PZT. We do have the dimension, all the dimensions in millimeter. And right here, it's the density and modulus of elasticity which are used in the simulation. We can see like PZT 5A, PZT, as I said earlier, it's because of its anisotropic. So right here is the piezoelectric material properties. We do have, this is the relative permittivity, and we do have like, this is the dielectric constant, and we do have like right here the modulus of elasticity for the PZT is in the matrix form. Right here is just like a sample, the values, the numerical values for the piezoelectric material properties for the PZT 5A. And right here, as I say, I'm using like finite element method. So we use the meshing. We do have two different meshing for the solid 186 and the solid 187, because this one is take care of they would take care of the interaction between the fluid and solid. And also we do have like two different fluid elements, which is fluid 220 and fluid 221. The boundary condition includes apply an excitation voltage in the form of sinusoidal wave applied to the actuator, restrain the plastic holder for the actuator, and make the sensor hold free to move laterally to investigate the effect of distance on the wave propagation. So before I start, I think I may mention, I mentioned earlier, like we have like, I'm gonna use two-way fluid FSI, which is fluid structure interaction. Right here, okay, I'm gonna performing a harmonic analysis for the actuator under the excitation voltage in the form of V0 sine omega t. Performing acoustic analysis includes the fluid medium obtained from the harmonic analysis. Perform a second harmonic analysis to the sensor. Right here, just like a video how it works. So if we see like the right hand side is the actuator, okay, and we can see I applied the voltage in the value of 0.5 volt, and and like a frequency range which is much the experimental, and we can see like right here just like 3-dimension. We can see again how it works. So I apply a voltage in this PZT, which is the actuator, okay, and we just like monitor the acoustic pressure due to the excitation voltage. The numerical result usually include the total deformation for both sensor and actuator. And we can see like this figure shows the left hand side shows the deformation for the actuator. The right hand side, we see like we can notice the deformation for the sensor, and we can see usually, okay, the deformation at the actuator is higher than the deformation at the sensor. And this one for the circular, and this one for the triangular. We can see for all three figures, we can see usually the deformation is maximum at the edge and minimum at the center, while for the sensor, the maximum deformation occurs at the center, okay, and it's gonna be like it's gonna be less at the edge. Right here, okay, we can see this figure shows the acoustic pressure of the actuator on the left hand side and the acoustic pressure of the sensor on the right hand side, and the distance between the actuator and sensor. And we can see for the most cases the actuator, okay, there is a decay between the sensor and actuator. This is I think for the square, this is another figure show us the acoustic pressure variation with the distance, and we can see again, okay, the decay. And for all these three cases, we can see, okay, the PMN32, the PZT is higher acoustic pressure than the others. The experimental results, let's go to the experimental results. The experimental results usually, okay, it's supposed to be matched to the numerical. So I'm gonna usually, okay, this is both like the sensor and actuator, and we can see like we fixed one and we move freely the other one to measure, okay, the gain right here using the impedance analyzer, and we get the results right here. Okay, the experimental result. The experimental result usually, okay, as I say, it's just the gain versus the frequency, and we can see like at different distances. We can see there is like a peak, and all these peaks, okay, occurs at the resonance frequency. So right here we do have like two different figures, one for the glycerin and the other for the water. Or that result validation. The validation include the measurement, okay, of the gain for both the glycerin and water with the acoustic pressure, and we can see from these figures that we do have decay for both experimental and numerical. So the final after we make all these like investigation, okay, and right now, okay, we're gonna fabricate and fabricate a sensor that help us to measure the viscosity of the, like, as I said, okay, the main goal to fabricate the viscosity, okay, and used for the healthcare. So when I say like viscosity, because usually, I mean, okay, these sensor usually first of all used in the lab, and the other thing, it's super expensive. So that's why we fabricate an expensive device that helps in the urgent care. This urgent care, they usually use like these like the sensor to measure the viscosity. For example, if any incident happened to like, you know, a person, so for that, okay, like usually if any, like the person diagnosed with the chronic disease such as like diabetes, so usually this help us, okay, to differentiate if this like person is like diagnosed with a chronic disease, or so we can that can help us, okay, to give like to give a heparin. Right here, okay, the design after many consideration. Right here we can see like the design of the sensor, okay, and supposed to fit in this vaccinator, which is help us, okay, when which help us to find the viscosity. Right here, okay, it's just like two PZT. This the PZT, and the other side we do have like another PZT, and we do have like this attached to the probe and soldering, okay, so we can measure the signal from the actuator and sensor. So right here it's just like schematic diagram how it works. We're gonna input like a voltage, a sinusoidal like a voltage to the actuator through the fluid, and by using the acoustic pressure to the sensor usually sense the signal and go to the gain phase analyzer to analyze the signal. The experimental results for the sensor, okay, is usually measuring the phase shift for the different glycerin. We are not allowed here to use the blood. That's why I used a mixture of glycerin and water to use instead of use the blood. So right here, okay, we do have different concentrations, start from 0 as a pure water, and we do have like 100% glycerin, and we can see all these measured using the signal impedance analyzer. Right here, okay, we can see all these points represent the experimental results, and we can see most of the point, okay, occurs in the 95% confidence level. So after we did the results, we need to correlate the viscosity to the frequency shift. So right here is just like experimental equations that usually, okay, usually correlate the viscosity with the frequency with all these constants. And this right now, okay, we need to do the same thing as we did in the numerical. So right here, okay, we use the probe, okay, with the PZT, and we have like fully immersed with a fluid. This is the probe, okay, with the dimension. Right here, the mechanical properties for the viscosity probe, the hollow brass, the copper, and the PZT5A. And the setup will include apply the excitation voltage in the form of sinusoidal wave applied to the actuator. We strain the top of the probe to be consistent with the experimental U. The deformation in the X and Y and Z direction equals 0. The solver include the model acoustic analysis, which is calculate the mode shapes of vibration for the probe and the surrounding fluid, and the harmonic whistle analysis using the two-wave fluid structural interaction FSI to find the phase shift for the actuator sensor PZT pair under the excitation the excitation of the applied voltage. Just one more thing. For the two-way fluid structure interaction, I mean, usually we do have like two types. The first type is the one-way fluid structure interaction, which is usually, okay, we used like just the deformation of the PCT. We model the PCT in the air, and then we transfer the data to the fluid. So that's why it's called like 1 FSI, while 2 FSI it include the deformation and the acoustic pressure. So we use like one solid, which is stronger than the one-way fluid structure interaction. Right here, okay, the numerical result shows the natural frequencies for the probe. When I say natural frequency, I mean I don't have any load. I just like model the probe. So with immersed in the fluid. So right here we have like natural frequency for the probe at different fluids in hertz. So we have the air, we have the water, and we have the glycerine. So usually all these correlated to the density and speed of sound. I would have like mode 1, mode 2, and mode 3. Numerical and experimental result. This figure shows the comparison between the numerical and experimental. We can see like all these, okay, almost like the same pattern for both experimental and numerical results. Right here, this figure shows the viscosity in centipoise versus the frequency, and we can see we do have like almost match for the model and experimental results. The conclusion. So in the conclusion, non-destructive evaluation method detecting the fluid property is demonstrated. Wave traveling through the viscous fluid media based on a signal traveling between the actual and sensor piezoelectric pair for different piezoelectric and geometries is investigated based on two-way fluid structure interaction using ANSYS. Numerical work is validated with the experimental work using two circular actuator sensor manufactured with a PZT 5A immersed into a large container filled with the water and glycerine. The result shows that the maximum acoustic pressure can be obtained by using the square piezoelectric pair fabricated with the PNN32. The results also show the pattern of decay for both numerical and experimental result in a good agreement. The numerical decay are 10, 8.25, and 8.4 for the water and glycerine respectively, while the experimental are 8.254 and 18.45 for the glycerine and for water and glycerine respectively. The conclusion: the actuator in the viscosity sensor is excited by 0.5 voltage alternating current sinusoidal waves with the varying frequencies ranging from 100 Hz to 40 megahertz. The phase shift is recorded for different concentration of glycerine and water to simulate the different viscosity ranging from 1 to 100 centipoise. The results also shows that the phase shift increases with the viscosity of the fluid. From the model analysis for the viscosity sensor, the results shows that the first, second, and third modes of the device are in the range of 648 to 2,358 Hertz for the air, 500 to 1,080 Hertz for the water, and from 469 to 625 for the glycerine. For the harmonic acoustic analysis, the result shows the highest frequency and the maximum gain occurs at the ultrasound range from 6 to 9 megahertz. Conclusion: correlating the phase shift and viscosity is found, making the probe a visible device for measuring viscosity. Is an expensive, small, and hence disposable way. Recommendation for future work: study the effect of piezoelectric polarization. As I say, I used that just like I excited the actuator in the Z direction. We can flip the direction, we can use Y direction, we can use the X direction, okay, and see the effect. Because if I change the direction, the polarization direction, the dielectric constant will be changed, and this will for sure will affect on the results and compare it with the current studies. study the effect of the fluid height level and fluid volume on the results, include the wall effect of the containers and compare to the results. They study the effect of using two different piezoelectric materials and see their effect on the results, investigate the effect of the temperature on the results, especially the temperature affect both piezoelectric material and the fluid. And as we know, usually the temperature will affect for sure on the piezoelectric, and this will give us different results, okay, and we can investigate it for the fluid properties such as viscosity and density. The unique contribution structure health monitoring is expanded to include the fluid using the same principle of wave propagation in solid, build a correlation between the fluid properties and frequency phase shift of the actuator sensors piezoelectric pair. This is the application. I do have like one, and the other one is ready for submission. I think we're gonna submit it. I don't know like exactly, but I think it's almost ready for submission. We do have like third one. I'm working right now on it, which include the effect of the PZT like geometry and like all these, as I said, all these like changes, so we can see the effect of these changes on the results. Okay, thanks for the attending, and please, I'm ready to receive the question. Before I receive the question, please, anyone, like if you have a question, just introduce yourself, like yourself. Okay. This one?
لا.
Right here?
analysis of variance جدول كان بالازرق. نعم اتوقع هذا قبله.
هذا.
لا قبله. قبله.
Oh, this one? No. Okay.
لا.
This one. This one?
اي نعم
Right.
هذا. هاي الدراسة الإحصائية اللي هي تتعلق بالتاكوجي ميثود وجماعته، حضرتك يمكن تكاتب analysis of variance. يعني بس اريد اسال على شغلتين. اولا الاورثوجونال اري اللي اختاريته اللي هو يتعلق بالمتغيرات عددهن والرينج مالتهن، ايش قد ما موضحها؟ يعني الماتريكس ايش قد اختاريته؟ او 9 27
اوتوماتيك؟ هذا اوتوماتيكلي. بس حضرتك دكتور عصام؟
نعم
دكتور عصام. هذه اوكي، اني استخدمت
ما ينتاب ممكن
استخدمت سيجما بلوت.
نعم
اوكي، سو سيجما بلوت عندهم دايناميك اناليسيس، انت بس تخلي البارامتر اوكي يو ويل جيت ذا ريزلتس.
بالضبط، لكن البارامتر تعتمد على الماتريكس اللي انت تختار، اللي يعتمد على عدد المتغيرات والرينج لكل متغير.
احنا عندنا اي طبعا اكيد موجوده. احنا قلنا من البدايه اوكي، احنا حصرنا المتغيرات حسب البلوتس. اوكي، usually you will get the result from the plot. So the range of the frequency, it's like, for example, okay, we have the viscosity and we have the frequency. Is that correct? You have the initial frequency, and if you see, I can show you. So this one, the viscosity, and you have this one is the resonant frequency, and this one is the initial. So you have the viscosity. Okay.
Yeah, but what's the range of the viscosity, for example?
For example, the viscosity
that you work on it.
Yes, it started from 1 centipoise, and you know, like 1 centipoise equal 0.001 Pascal.
Okay.
To, I think 60. It depends on your range. So for this case, it's I think 1600, means 1600 centipoise, and the frequency range it's from we started from 100.
Yeah.
100
I think it was better if you put at least one slide more to represent these parameters and the range, because since you showing this is a slide, so you have to show us the basic of this result, which is what I said before. They called orthogonal array or OA. This is first.
For this one, I don't use like, I think I use the Gaussian.
No, I understand exactly, because this is like exactly a statistical work, which all our engineering is mostly far away from this.
Yes, we are lag.
Yeah.
Okay.
Yeah, exactly. But since you showing this slide especially, so you have to show at least one or two more slides represent of us the range and the parameters you selected to show us this result. This is first.
No.
The second, do you know what the P parameter meaning? For example, in this table, P parameter equal 1, 1, 1. Do you mean what the meaning of the P parameter was 1 or 0.05, for example?
You mean the definition of parameter or what?
Yeah. Now we see P parameter is 1, number 1.
Mm-hmm.
Do you mean what the meaning?
I don't have any idea about the these parameters, because usually, as I told you, we just got like these from.
I see, because some of these results give us the mentioned about if the error range between practical and the statistical work is acceptable or not.
Mm-hmm.
So I advise you to go deeply to just try to understand what the meaning of P and T parameter, standard error, as you see, because these numbers is very important. For example, if you try to publish a paper, especially working or especially trying to showing the result, these numbers, for example, so you have to get lots of feedback asking about the meaning of these parameters and the number. You know?
Okay. Thank you.
And thank you. Other results, it's very interesting. And as I said before, the whole work is very interesting, and I hope you successful life after your graduation.
Thank you.
Thank you, Dr. Nasr.
Thank you, Dr. Assam. Good question. Just one question, Dr. Ahmed. You make some confuse in my mind, because I am teaching the non-destructive testing and non-destructive evaluations for postgraduate students. So in ultrasonic tests, there are some sensors used called double D. You used 3 structures: circular, rectangular, and triangular. Yeah. Square, circular, and triangular.
Okay.
And and your results good or best in square. Yeah.
Yeah, it's based on the square.
It's the best one. Okay. But the double D is more accurate, and the double D means that the circular sections, because a double D means a half of circle may make like actuator, and the other one like as a sensor, just like your jobs. Can you explain why square and circular is in far sensors used?
I don't think I understand your question. So when you say like just half, I mean when you say like half circular. When you say what do you mean by that?
Double half. The sensors, the sensor structures is double half. Double half mean that double half circle and half circle. The one half circle, or the first half circle, used as actuator, and the other one used as a sensor. And this instrument
is it separated when you say that, or just like connected to each other?
Both of them in one sensor, one sensor structures. One send the wave, and the other one receive the results of the.
Have you seen like one of these?
Yeah. It is used in medical instruments, used in hospitals, like the pregnancy test for child, boy or girl, the size, the positions of the children, and so on.
Okay. So I mean, so is it like? I mean, when you say like half, and then is it immersed in the fluid?
The media is glycerine, because they used glycerine in the body of the pregnancy women.
Okay, so when you say glycerine, and how it works, I mean, so I think you mean it's not like connect, it's like you say semicircle, okay? When you say semicircle, semicircle, and it's connected to each other, so you can send like a signal. It depends. Let me tell you something, okay? It depends on the application. So we usually, I mean, we works, we do have another, I agree with you. We do have another semicircle but it is totally different. Okay, I think what you mean. So when you have like these, okay, and it's just like separated. It depends. Okay, it depends on the application.
Yeah. Okay.
So for me, okay, I just like investigate. Because we do have like, we try, okay, to fabricate inexpensive and a small device, and this is, by the way, this is disposable. So we use it just like for one time.
Oh, that's good. That's good.
Yeah, I mean, it's usually, I calculate the cost. It's just like $10 even. I mean, maybe less. Okay, just like, you know. So that's why I use I mean, I need to fit it in the vaccinator. Okay, that's why. I mean, I do have. I saw like this. I agree with you. I saw like this one before, but I don't know how it works. So is it like one? It's an annular. When I say annular, means like we do have like two. Okay, so I'm not quite sure exactly.
Okay. Another thing, Mercedes-Benz used this sensor, or used like this sensor in Siegelberg model that's produced after 5 or 6, after 10 years. They use these sensors to give a reader about the viscosity of the lubricant of engine.
That's correct.
Okay. Then, and also give the increasing or the temperature sensing of the oil of the engine. I think your job, it is nearest for this job, because your sensors measure the density, measure the temperature, and you compare between the effectiveness or the accuracy of the piezoelectric materials with the temperature and viscosity, and so on. Yeah.
Okay. Let me tell you something. Okay. So let me tell you something. Okay. Usually, okay, I mean, most of the sensor right here, they use the single PZT. So how it works? They usually, when you say like, I read about like this. Usually, okay, most of the company, they use like single PZT. How it works? So they immerse like the single PZT probe. Usually they make it like attached like to the beam or anything, and immerse like in the oil, whatever it is, and then they correlate it to deformation. They usually use the laser vibrometer, Doppler, and this one they usually measure the deformation, and they correlate the deformation to the like the viscosity. Okay, whenever you have like the resonant frequency, so they say, okay, this one, they correlate usually the deformation with the viscosity. Right here it's totally different. That's why if you see most of the sensors that you talk about, they usually works in the low frequency. Just check it, and you will see like
I know that.
So most of them they use like with the frequency range. I work in the high frequency range.
I see it.
If you check the range, you will see my range. Okay, is from 6 megahertz. I sweep. I use the analyzer, so I sweep from 100 hertz to like I say like, because the capacity it's up to 40 megahertz, and I didn't see anything in the range of the hertz or the kilohertz. That's why, I mean, the only thing, okay.
I know that.
The principle is the same. Okay, the principle. We usually work
the
on
same
the principle. So the principle the same, but we do have different application with like different parameters.
Thank you very much. Okay, نفتح باب الحوار للجميع. الذي يسأل يعرف نفسه ويتفضل بالسؤال.
Mr. Dean, do you have a question?
دكتور عادل.
شكرا دكتور نصري، شكرا دكتور احمد تقديمك الجميل والموضوع حقيقه يعني انا اختصاصي كهرباء، لكنه شيق وفرحت انه اشوف من الفاينات اليمنت، اشوف الانسز، يعني احنا اذا مو بعيدين ان شاء الله عن العلم حسب ما يتصور البعض. انا ما عندي حقيقه سؤال، بس اطلب من الدكتور احمد، احنا عندنا مؤتمر بالاي او بي سكوبس، يا ريت لو بحث انت والمشرفه باسم جامعتكم هناك، هي باسم الجامعه الامريكيه وانت باسم جامعتنا التقنيه الوسطى، حتى يكون مشترك، واكون ممنون. شكرا جزيلا.
اوكي.
دكتور احمد، انا بس جست يعني عندي المام شويه بالاحصاء او بالبرامج تستخدم بالاحصاء. ان حسب ما فهمت من دكتور عصام من مداخلته انك استخدمت الانوفا.
لا انا ما استخدمت الانوفا، انا استخدمت I used like a software called Sigma Plot. Okay,
Sigma
and
Plot.
right now I'm gonna use another one, which is, as I told you, okay, we do have like third paper, which is we use like a software called GMP is very amazing software. They help you. For example, I will tell you example. Okay, if you have like for example right here, if you have like PZT and geometry, you have like the dimension, thickness, diameter, like length, and you have like, for example, you have like frequency, and you have like fluid level. So if I want to use like what we call design of experiments, so what you did, you create for example, you do have like 3 different geometries. So I do have like 3 different geometries. You have like circular and rectangular, and this is not parameters. This is just like input. Like for example, let me call it like L1, L2, L3. Okay, and we do have like numerical. For example, frequency range. You do have like the diameter for the PZT. Okay, you have like fluid level. So you can put all of them in the design of experiment, and you see what parameter will affect on the others. For example, you have input and output. You have input, you have the output is the acoustic pressure. So you will see all these effects, like for example, as I say, like the different variables on the acoustic pressure, and see which is dominant. And you can correlate the acoustic pressure, for example, with the distance between PZT, with the viscosity, with everything. Okay.
Okay.
I use it before. Okay, I use it like this jump simulation. It's very amazing. I think it's better than Excel or I think we do have like and the Sigma Plot, but I usually prefer to use it and jump the jump.
Yeah. That's good information to me. Thank you very much, Dr. Ahmed. Dr. Adil, بما أنه no one ask, تسمح لي أن أريح دكتورنا الغالي إن شاء الله يرجع بالسلامة وبفضل الله.
Thank you so much. I appreciate it.
You're welcome. And أنهي الجلسة حتى يأخذ بريك ويرتاح الدي، وإن شاء الله نشوفه عن قريب. وأول ما يوصل أرجو من حضرتك أو من حضرته أول ما يوصل أحب أرحب به شخصيا من قدومه إن شاء الله إلى بغداد بإذن الله.
Thank you so much. I appreciate it.
أشكر الجميع.
شكرا جزيلا.
شكرا دكتور عادل. ننهي الجلسة إن شاء الله. تحياتنا للجميع
شكرا جزيلا.
أشكرك. مع السلامة.
شكرا دكتور احمد، شكرا للشعبة العلمية، مركز الحاسبة، للجميع، الاستاذ الدكتور نصري، شكرا للجميع واتمنى لكم التوفيق.
Dr. Luay, is that recorded?
Yes.
Okay. Would you please just like do me a favor and send me like a copy of this recording? Just
yes,
for
indeed. Yes, indeed, Dr.
For all, Mr. Luay. For all.
Yes, indeed.
Thank you. I appreciate that.
I appreciate so.
You're welcome.